I will going to talk about my past and future research concerning our central star, the Sun. But before going to the Sun, let me say a few words of my career, even though Jari said already something. But when I was young, I had two interests above all else. One was programming with my Commodore 64, and the other was going out during the night to look at stars. And my mother used to tell me that your hobbies are completely useless. You should become a doctor, so do something useful. But I kept my resolve, and I told her that I will study astronomy, physics, and computer science, and I did. Well, I studied during the same time as massively parallel supercomputers emerged. So I ended up then, I was hugely fascinated by this possibility, and I saw huge potential for my research in this, like distributed parallel computing. So I ended up more or less writing the first parallel algorithms for computational astrophysics, and I didn't do so much astrophysics. So I ended up there. So I was kind of having an astrophysics degree without really being an astrophysicist, like in the interim gray area between computer science and astrophysics. And I got a huge, big identity crisis from that. And I almost quit. And I was almost thinking that now I go back to my mother and tell her that you were absolutely right. But I was possibly too proud to do that. So 20 years I juggled painfully between these two fields. But then something extraordinary happened. I heard first from US, but then also from Europe, that there is now a new field of science called astroinformatics developing. First, it was, of course, more like big data coming from the observations and observatories, machine learning, data mining. But I was thinking, hey, I'm doing high-performance computing, but I can be an astroinformatician as well. And I just said, yes, I am now an astroinformatician, and it was remarkable what this kind of just deciding to be something and not anymore being in between anything helped me to solve this identity crisis. And since then, I have done nothing conventional anymore. I have now I'm doing more computer science than astrophysics. But of course, I share the passion that I had as a child for astrophysics. But my passion today is really to develop high-performance computing tools for science. Right, but now I still have this passion for the Sun, and let's now talk about it. So, Sun is, of course, behind the existence of life here on our planet, and without it, life would not exist. So that's why, for example, ancient Egyptians worshipped it as a powerful God. So it gives us life and warmth. So am I talking about the Sun because it's ceasing to shine or what? Of course not. The Sun is a relatively boring, small, middle-aged star that has been shining for 5 billion years, and it will continue to do that for 5 billion years more. So that's not the issue. So what is the issue for us then? Well, we are no longer ancient Egyptians. We are now living in a society that is based on technology that is highly vulnerable to the electromagnetic disturbances that the Sun is all the time causing. So this, we call that bad space weather. So whenever the Sun decides to erupt, then we can expect to have high energy particles and electromagnetic radiation that cause disturbances in all these infrastructures here, like power grids, navigation systems, communications, and whatnot. So that is the reason why modern human beings should be worried about the Sun. So what actually causes these eruptions as bad space weather? It is directly related to solar magnetism. So the Sun is a big magnet, even though you cannot really see the magnetic field, but it makes the sun to erupt and release the huge energy that it is storing. For example, in a solar flare, which is the bright features on the solar surface behind me now. These solar flares are perhaps the most dangerous events that the sun can cause. They occur in minutes. They release electromagnetic radiation across the whole spectrum. And as we know, electromagnetic radiation travels with the speed of light. So these will come in 8 minutes to the Earth. Sometimes flares are also associated with coronal mass ejections, which are actually a lot of charged particles that are also ejected to the interplanetary space. They arrive slower, but they are also as dangerous. So this is the solar, a direct effect of solar magnetism on us. So what is then driving the magnetic field? Well, the roots of space weather, they lie in the solar interior. So the sun is a star where there is hydrogen, helium, and heavier elements, which are fused into energy in its core. And then the released energy is traveling through the radiation zone, roughly 70% of solar radius, until it reaches the convection zone. Well, convection is just heat transport by mass movements. It's like a boiling kettle, so you have bubbles that transport heat upwards. And as we know, or perhaps we all remember from school, that according to the laws of electromagnetic induction, whenever we have charged particles moving as they are in the sun, rising and sinking bubbles, you will generate magnetic field. And this is the mechanism, basic mechanism, how the magnetic field is generated. But all the details, how exactly the solar magnetic field becomes as it is, and how does it form concentrations and how does it erupt, we do not yet understand. Right, so, well, the sun cannot be put into a laboratory. The conditions are so extreme. On the other hand, we do not have any analytical theory that would describe a plasma as complex as the solar one. We know an analytic theory for water, and that's more or less it. But the solar plasma is really compressible versus the incompressible water, and it is also at extreme temperatures and densities. So basically, what we can do to understand the sun is twofold. Either we make a numerical model of the sun, or then we try to deduce all this information from observations, because we can observe the sun. What I do and where my research comes into play is in these computational studies. And making a computational model of the sun is not very easy either. So it requires a lot of computing resources. So the place where we can run such models is actually the biggest supercomputers around the world, like, for example, the LUMI supercomputer, which is depicted here. So these are extreme scale numerical models, and now I'm going to show you what we have learned from them so far and what is still wrong. So in Aalto, we have developed a very powerful in-house kind of toolbox of high-performance models that we can use to model the sun. So I guess on this side, you see our models at global scale, where we actually model the whole sun or the whole convection zone of the sun. And on this side, you see some local models where we can model sunspots and coronal structures, and of course, with higher resolution, also some structures within the convection zone. And all these models are developed in such a way that they can be efficiently run in these LUMI-like computers. And here is one example of a simulation. This is a local simulation, and the computational domain is located in the bottom of the solar convection zone. And this is the velocity field from 2D slice of that flow. So this is a highly turbulent flow. The Reynolds number is several tens of thousands. So extremely turbulent, and we are here close to the solar parameter regime. And what is extraordinary in this simulation is that we could show that this kind of a flow will generate and maintain very peculiar magnetic fluctuations throughout the solar convection zone. This is world's largest simulation of its kind. It's 8,000 cubed and goes down to closer to solar parameters than ever before. And these are the peculiar magnetic features. This is not a movie, this is simply a snapshot of the magnetic features. And now it seems that the full solar convection zone from bottom to top is filled with these kind of structures. And the funny thing and most extraordinary thing of these fluctuations is that they also contribute to the global dynamics. Even though they are very small scale, they have a global scale effect. That's called inverse cascade in turbulence research. Then, of course, we have plenty of observational infrastructures. For example, this high-node satellite. So it has been observing the sun for years, so we have years and years and years of data from, I think, more than 20 similar satellites. And we can see the magnetic picture in detail, like here, a sunspot which is an intense concentration of magnetic field. So intense that it is inhibiting radiation. So this black area there is the concentration of the magnetic field. So with all this observational data and with all these models, where are we actually currently? So the current approach is to make observations somewhere and a model elsewhere, and then we do them kind of in isolation. They are not talking to each other. And then when the simulation is ready, then we compare it to observations. So here we have the largest global simulation of the sun ever made by us a few years ago. So you can see that there are some similarities, but we do not really at all see a sunspot-like structure there. So then how to go forward? We are not capable of reproducing observations, and of course, due to that, we have a very low predictability from these models. So how to go forward? Well, maybe 6 months ago or a little bit more time ago, I came up with the concept of a digital twin. And what is the essence of the concept here is that we should not anymore do the models and observations in isolation, but we should start building data-driven models, which is the idea behind a digital twin. Because it's a set of adaptive models that really emulate the behavior of the physical system and update themselves or itself based on the real-time data. And when you can really replicate the physical system, then you can ask interesting questions, like what if? What if physical conditions change? What is the response? Or conversely, if we see some event on the sun, we can ask what is the physical cause with the help of the digital twin. And this definition originates from NASA Apollo missions, where a digital twin or replica of the lunar module saved the astronauts. Maybe you know the story. But the solar digital twin is therefore a concept where we combine the observational data with the models so that the models are updated based on the observations. And what we are after is that because the model is driven by the data, it must be optimized to produce the observations in the first place. So we will no longer have the discrepancy between the observation and the model. And hopefully this will then enable more accurate predictions of space weather and its long-term effects, what we call climate. And then we hope to study what-if scenarios. Of course, this is not easy, extremely challenging. We are not rid of these extreme scale computational challenges, and we are bringing in moreover, the data analysis challenge here, but I'm an astroinformatician and I'm on it. Thank you.